not just talk about a neural network which is given, and then we just calculate how it behaves if I put in some data and what do I get out. But actually the main point of neural networks, of course, is that they should learn something. So I mean, it's not, the configuration is not a given thing, but it should be changed according to what function it should represent. I mean, of course, a neural net should represent a function, but you don't know how to describe this function. You only know that for some input, it should give you this output. And from this, you should, in an algorithmic way, get your net. Okay, and usually the algorithm for doing this is gradient descent. Okay, so I want to talk a bit about this from various perspectives, very general one. Of course, I mean, these are things which are getting more and more complicated, and it's harder and harder to get precise results. Good, okay, but let us go back to our random feature model. So because that's maybe the one of which we have quite a good knowledge. So I mean, our random feature neural network, which actually should describe a function. So what is this? I mean, so we get an output if we have an input. So we have input matrix, we apply f, and then how do we calculate the output? I mean, in principle, what we looked at was the feature matrix. We calculate the features of the inputs, which we calculated in a random way, namely essentially we took sigma of, let's say, W1 of x. So this is somehow the first layer, first hidden layer in a network. But then, of course, I mean, I should now, from all these features which I calculated, I go back by a linear combination of them to R. So I mean, my functions are usually just real numbers. So I also apply here a W, little w. So this is a vector which I write as a row vector. So it's in 1 times m, and my data matrix is in p times n. So my data are p-dimensional. I have n of them, and then I have here this weight matrix, which is in R m cross n. So I'm calculating m features out of my data, but usually in a random way. Good. Okay, and so. What we have done up to now, we have looked essentially on this thing, and maybe, okay, then we also understand this, but from the point of view, I mean, I'm putting in x, and usually I'm putting in just independent Gaussian things, and then the question is, what do I get out? So essentially, we understand if I have here some x, or maybe at least some very nice x, I understand what I get out here. The statistics from here, I can control somehow the statistics there. So that was what we did up to now. But there, of course, I mean, this W and this W1 are somehow given. So I mean, the W1, we also said this should be a Gaussian random matrix. So the statistical properties, maybe we go in this direction. So maybe I start here. So the statistical properties of x. From this, we can maybe calculate, understand the statistical properties of the output of y. Good, but now, of course, now we want to go more in this learning direction. So actually, this guy here and this W1, they are not, I mean, we should find them in such a way that the net produces what it should really describe. So namely, for a given x, so we should know the output, which I usually denote by y hat. So this should be the function applied to my vector x, for example, my Gaussian random vector. But I prescribe the output, and now I want to know what are little and capital W's for producing such a thing. Okay, so we should essentially learn the little w and the W1 such that my net describes this situation here. Good, okay, and so this is the learning feature. Okay, and in this setting here, I mean, I have now I mean, I have this little w and I have the w1, and somehow I have two possibilities I can look at this. So we could say, we fix the w1, this is just my random matrix, for example, and then I just want to learn the best little w. Okay, and so this is a property which, okay, maybe it's not the one which we really want, but at least it's good to understand this. So deterministically, so we could fix this w1 in a deterministic way, or more in our setting randomly. So we choose our random guy. Okay, and then we only learn the little w. So we want to choose the w in the best way such that we get this one here. And only learn the little w. And this, of course, is this regime of linear regression. So I mean, we know essentially the output here, and then we want to find the best guy here. This is linear regression. Linear regression, not on the data matrix, but on this feature matrix. But this feature matrix is just a new matrix which are given and which we understand somehow. Okay, but this is linear regression, which of course is quite old subject, and more or less everything is known about this. And of course, I mean, the power of neural nets is not just linear regression, but the point is you should learn more, namely you should also, for example, learn the W1, which means you should do a feature learning. I mean, you should learn which features are good ones, which you should calculate. I mean, if I just put in the W1 in a random way, because I don't know how to do it, or in a deterministic way, because I have the idea, I know what are good features which I should consider to distinguish cats and dogs, for example, then, yeah, these are given, I'm not learning them, I have to tell the net which features it should consider, and then I just make the best linear combination of the given features. Okay, but feature learning seems to be the real thing which gives the power of neural nets. So I mean, you should also at least allow that W1, and of course if you have bigger neural nets, then all the layers, all the W's there, they should learn, they should be adapted. Okay, so I mean, so in our context, the maybe more interesting thing is that both the little w and the W1 should learn. And this then at least allows the possibility of feature learning. Yeah, good. Okay, and now, of course, the question is, yeah, how should we do this? And for linear regression, I mean, we talked about this a while ago, and essentially for linear regression, we have an explicit solution for the best function which approximate this. But of course, in general, we don't have an explicit formula. So this means, in particular, here in this case, we cannot write down the formula of W1 in terms of the data. And so what one usually does is an algorithmic way for learning. So you need an algorithm which maybe starts somewhere, and then maybe you change your W's in some incremental way. And the usual algorithm for this is gradient descent. Good, okay, and even in the case of the linear regression, a gradient descent has some meaning. So maybe what I'm doing now is, again, I'm going back to the maybe trivial thing from the point of view of neural nets, but at least the thing where mathematically things are quite clear. So we are looking again at linear regression from the point of view of gradient descent. And then maybe next time or so we try to go further to the feature learning thing. Good, okay, and so yeah, let us go back to our linear regression problem, which we did in chapter 6. And essentially, I mean, this was solving linear equations, but there you have to distinguish between the underdetermined and the overdetermined case. Okay, and for us, for our neural networks, it's usually the underdetermined case which is maybe the more interesting, because this means this corresponds to the overparameterized. You have many parameters, you have more parameters than actually you would need to describe the thing. And this seems to work quite well. So maybe we are looking again on this situation now from gradient descent. So in this case, we know what is the best solution, but we want to see, whether we can get it in algorithmic way. Okay, so yeah, so let us go back. To linear regression. And mainly we will consider the underdetermined case. Determined or over-parameterized case. Okay, so what is the situation there? So there we are given, essentially for this I can again forget about this. So essentially I'm given the x and I want to and I want to find the w such that I reproduce a good solution. So I'm given x, I'm giving my input data, and then I also am given the y hat, which is the output, which should be the value of the function applied to this guy. So the y hat is just a vector. So I'm putting in, for each column here, I get an output, and my function should reproduce this output. And the functions I'm consider are just linear functions, which are described by w, and I call it now w hat because that's the one which I'm looking for. So this is a 1 times p matrix. So it's a vector such that y hat is w hat times x. Good. Yeah. And in our case, the underdetermined case corresponds to the fact that n is less than p. So I don't have many observations. Yeah. No, what is it? M times p. Is this better now? Yeah. Okay. So if I multiply them, okay, I'm multiplying over the dimension of the data space. Okay, and I get a 1 times m. Yeah, and then I multiply it with this, and then I'm getting out a 1 times n matrix. Okay, the sigma, of course, doesn't change the size of the matrix. It's just applied entry-wise. Good. Okay, so the underdetermined situation is if I have only few data points, observations, but the dimension is bigger than this. Okay, and so, of course, the picture, of course, is I have here my r to the p, my data vector, and then I just take a linear combination of those guys, and this linear combination is given by this w. This is just the vector of the weights, how I weight this. I take the linear combination, and then I get out something in r. So if I have put in here a vector x, then I get here a y, which is w hat times x. Or usually, I'm putting in not just one x, but I have n of them, and I collect them in my data matrix. So I'm putting in here my data matrix x, which is just a collection of n datas, and then I'm getting out n y's, but I also collect them in a matrix, but in this case it's just a vector. So namely the y is then just w hat times x, and the y, of course, is just the matrix of y1 up to yn, where y1 is the image of x1, and up to yn is the image of xn under this mapping. Okay, so that's the situation which I want to consider. Yeah, and x x and y are given, or the y hat are given. Yeah, or maybe in this generality, maybe I just put a w here, and then I want to look for the w hat which corresponds with the given data. Good. Yeah, and now, of course, the interesting thing is in an underdetermined case, so I'm given y hat and x, this is a system of linear equations, but this system has more variables than I have equations. So this means the solution is not unique. And usually, I mean, we're in a situation where a solution exists, but then there are infinitely many. Okay, and then of course the question is which one should I take, which is a good one. And in this linear regression we talked about, there was somehow a prescription which one you should take. We could write down a formula, but we also could characterize it by saying that this is among all solutions the one which has the smallest norm. Okay, and so this in a sense is considered as the best one. Okay, so in the underdetermined case, so n less than p, so there are typically, and this typically means that the rank of my matrix X has to be equal to n. So I mean all the equations which I have should be linear independent so that they cannot contradict each other. Of course I could take the same equation again and again but change the constant on one side, and then I would have contradictions. There would be no solution. Of course it can be that there are no solutions, but typically we have this situation. So there is one solution, but then this means there are infinitely many. Infinitely many solutions. And okay, the best. Yeah, we have to say what is the best, but okay, a good way of saying what is the best is the one which has the smallest norm. So I mean that's what I'm meaning here with the best. So it has the one with the smallest norm. This is given by, we could write down an explicit formula. So namely this W hat is the Y hat, and then I have X transpose X to the minus 1 times X transpose. Okay. Yeah, and I mean this is essentially the same solution as you take in the overdetermined case. I mean in the overdetermined case you have in general no solution, but then you can only approximate the given solution with the least square. Okay, and then you can write down a formula like this, but then you have this here the other way around. I mean in our case the problem is X is a rectangular matrix, and depending on in which situation you are, P is less to n or the other way around, X transpose times X is invertible, or X times X transpose is invertible. And in this case this guy here is invertible. Okay, and I mean it's easy to check, we did this, that this is a solution, and it's also easy to see that among all solutions this has the smallest norm. Good, okay, so in principle we can say, yeah, okay, we know here everything, so why bother anymore, that's it. Okay, so, but now of course, we want to understand this maybe more conceptually, and even from the numerical point of view, I mean you have to take here an inverse of a matrix, and this usually is a very big matrix, and taking inverses of matrices is something which usually you should never do. Better not take inverses of matrices, but try to do something else. And very often this something else is that you do an iteration. Maybe you do an algorithm where you do simple matrix operations and you hope that you converge to something. And that's exactly what we are doing here. But maybe let us also first note that we can also rewrite this problem as an optimization problem. So namely, of course, so our problem, which we want to solve, so namely our problem is that Y hat is equal to W hat times X. So that's what we want to solve. And we can also write this, of course, as saying that the norm of Y hat minus W hat times X is equal to 0. Okay, and so this means, of course, that the W hat minimizes the value of this quantity, because I mean the norm is always positive, greater or equal to 0. So if I found a value where it is 0, it means, of course, that this minimizes this. So this means my W hat minimizes this quantity here. So actually we have a minimization problem. Okay, and for minimization problems, of course, we can use calculus. So And of course, the minimization is given by a point where the gradient disappears. And then, of course, if I want to have a numerical algorithm, then of course the gradient gives me the right direction where I should go to improve my situation. That's why this is the gradient descent. I mean that's the simplest algorithm which we have around. So somehow the strange situation with these neural nets is that we are not developing very advanced and subtle algorithms for getting something, but that actually the most simple algorithm we can think of seems to work surprisingly well. Okay, but let us look on this a bit more concretely. Okay, so we can say the W hat which I have is actually a number or vector. So this minimizes y hat minus w times x. So the w hat is among all w's one which minimizes this, and of course it minimizes equal to 0 in the underdetermined case. In the overdetermined case, I cannot achieve equal to 0, and then the least square algorithm is really that I optimize this. So I'm looking for the best w which make this as small as possible. In the overparameterized case, it cannot be equal to 0, but I make it as small as possible. In the underdetermined case, it can be equal to 0. So in principle, I know that I have a solution, and I know what it explicitly is, but we want to consider it from the point of view of optimization. And okay, and so let me just multiply this out. Okay, let me take the square of the norm. So this is so this is a vector, and the square of the norm is the vector times its transpose. So this here is a column vector. So I have here y hat minus wx times y hat minus wx transpose. If I multiply it out, I get y hat transpose minus y hat. Then this guy, there I get x transpose, w transpose, then I get this term minus wx, y hat transpose, and then I get this times this, which is minus wx, x transpose, w transpose. Good, okay, and now, if I have a optimization problem, usually I should look on the derivatives. The first derivatives, they should be equal to 0. This characterizes minima or extrema, and in the multidimensional situation I should take the gradient. So what is the gradient of this quantity here? So the gradient with respect to w. W is the quantity which I want to optimize. So I take the gradient of w with respect to w of this guy here. So y hat minus w x squared. So this is just a function taking on values in R. So the gradient is just a vector. And I take the gradient as a row vector. I mean, you always have to decide if you take the gradient of something, should you write the gradient as a row vector or as a column vector, and it depends maybe on the situation what is better. So here I'm taking the gradient as a row vector. So the formulas I'm writing down, in the end I should get a row vector out of it. Okay, and so what is the gradient? Okay, of course this doesn't depend on w, so this is 0. Then I take the derivative of this and the derivative of this, and if I take the derivative, with respect to this, I mean, okay, it should be this or this. Here I have the transpose. So let me just say it is actually both terms are giving the same. So you have minus 2 times. In principle, this goes away, and then you are left just with this constant here, y hat x transpose. And this here is a quadratic expression. So of course, taking the derivative, you remove one of them, and you're left with the other. But again, it's w and w transpose. You at least you might be confused. What should I take away? What remains? And actually, you again get minus. No, here's a plus. It is minus times minus, so it's plus. So you get here plus 2 times, and essentially it is as if you take this away. W x transpose. So also here, you remove this, and you're left with this. But here the same. And maybe we should just think about this, just that we are absolutely clear about this, that this is really the right result. So namely node. So what am I doing here? So my W, let us write it in components. I mean, it's nice to have it in this compact form, but I mean, I have to say I'm confused. If I take the derivative of this with respect to W, so what is really the result? So I can only really be sure if I'm writing this in components. So W, my W is a row vector. Then I have the Y transpose, X transpose. So this is a vector, and this is also a row vector. So, and let me denote the components just by A1 up to AP. And then I have here X transpose, so this is a matrix. And I denote this, I call this A. So just shorthand notation. And the entries I call Aij. From 1 up to P, but you should note that this is a symmetric matrix, because if I take the transpose of this, it's the same. So this is the same as A transpose. And this is relevant that I get this result. Good, but now let me see with these notations. So what do I get? Let us first calculate the transpose of A, the gradient of A W transpose. So this is this term here, where the A is now just this vector. And so what is this? So this is the gradient with respect to W of, this here, this is just the inner product between A and W. So this is just A1, W1 plus AN, or AP, we are going to P here, AP, WP. And of this function, I take the gradient, so I get a vector where the first component is the derivative with respect to W1, the second with respect to W2, and so on. And I write this as a row vector. So this means I take the first guy is I take the derivative with respect to W1. This is just A1. The second is the derivative with respect to W2, which is A2, and the last is the derivative with respect to WP, which is just the AP. And so you get, I'm just getting back the vector A. Okay, and I mean that's what I have written here. If I take the derivative of this, I'm getting back this vector. This is here. Okay, and I'm claiming here I'm doing the same, but here you should observe that actually this guy here is the same as WAT, because we are here just real valued. So if I take the inner product, I mean this inner product, here you can say this is this is A multiplied with the transpose of W, or you can say it's the same as W times the transpose of A. So this means here I get the same result. Or I get the transpose. So if I have the W here, I get the transpose of this, but this is again this guy here. So I get twice this term. Okay, this is totally trivial, but I mean, okay. It's better to check those things. Okay, and for the matrix, so for the quadratic term, so what is this? So there I have W, A, W transpose. And the A is the X transpose, a symmetric matrix. So what is this? So this is the gradient. And now this here is just the quadratic form with the coefficients from my matrix A. So this is just a sum over I and J, Wi, Aij, Wj. Just doing matrix multiplication. Or vector times matrix times vector. Okay, and now I take the derivative with respect to W1 and then the derivative with respect to W2, and I write this down as a row vector. So let me write down just the first component where I take the derivative with respect to W1. Okay, so I have to check where do I have a W1. I have, okay, if the I is equal to 1, I take the derivative with respect to this. So I get, then I'm left with summation over j. I has to be equal to 1, derivative with respect to this. This goes away, and I'm left with the I is equal to 1, and I have here the j, wj. Okay, and then of course I also have the derivative of this guy, but for this the j has to be equal to 1. And then I have here the I, wi, and I have a I1. Okay. And now maybe I sum over I, but maybe because I just rename this to j, and then I just have a sum over j. Okay, and now you see that because I have a symmetric matrix, this term is the same as this. Here I have aij, here I have aj1, but because my matrix is symmetric, this is the same as a1j. And actually, so what I have here is 2wj aj1. Okay, so maybe it's better to take this form, because this is the product now of this vector with this matrix. And I take the one component. Okay. Here I have used that A is equal to A star. Yeah, okay. And so I mean for the other components I get the same, but so what I have here is I have this 2, and then I have just W times A. I mean this here is the one component of this. This is a vector, and then the others are the other components. And so you see I get exactly this 2WA. It's exactly what I have written down there. Good. Okay. So this was trivial, but it's always nice to do trivial things because that's something which one understands. Yeah. So where are we now? Yeah. So we see that if I want to optimize or minimize this quantity, I should find a W for which the gradient of this is equal to 0. So that's a necessary condition. So I should look for solutions of this y hat minus W x squared equal to 0. So for my double W hat, the solution which I seek, this should be equal to 0. And then this gives me, of course, the equation that the gradient should be equal to 0. So this equal to 0 tells me that this should be equal to 0. Or that this is equal to this. And the 2 cancels away. So what I get, so this gives what is then usually called a normal equation in this context, namely that W hat x transpose is equal to y hat x transpose. Okay. And this, I mean, in the overdetermined case, this has a solution. I mean, then x transpose is invertible, and I just can solve this for W hat. And that's the least square solution in this case. But that's a situation in which we are not so much interested. But just to have the perspective. So let me also write it down. So this gives the least square solution, which is just, I mean, bringing this on the other side, because this is invertible, so I can do this if I have maximal rank, which I always suppose. So omega hat is just y hat x transpose, and then I'm taking the inverse of this from this side. So I have here x transpose to the minus 1. So this is the solution in the overdetermined case. The overdetermined case. And I mean, that's usually how you do this least square solution. Okay, but in the underdetermined case, of course, we are not much better than at the very beginning. I mean, we have to find omega hat which solves this, but there are infinitely many. And now we have to say which solution should we take. I cannot invert this, but we can say in principle I take the pseudo-inverse. So I take somehow the best replacement for the inverse, and then we can also get an equation. That's the one which I wrote down at the very beginning. And we get the best solution in the underdetermined case, and then omega hat is, I write down the same solution, y hat x transpose, and then I take x transpose. I would like to take the inverse. The inverse does not exist, but okay, one has this kind of this pseudo-inverse, which takes as much as possible of the inverse, and the rest is more or less a set equal to 0. But in this case, one can show that this can be written down with the help of a genuine inverse if I just take here the other order. Because in the other order, this guy is invertible. So this is the same as y hat, and then I have here x transpose x to the -1, and this is now real -1 x transpose. So I bring this x transpose to the other side, but the effect of this, that here I'm exchanging the order of the transpose and the x. Okay, and we checked, even if you don't know what the pseudo-inverse is, this formula, that's the one with which we check that this is a solution and that it is the best solution. Okay, so this gives this in the underdetermined case. Yeah, okay, but now finally let's come to the algorithmic point of view. Until now I have just talked again and again about that we have a kind of equation. But now we don't want to just take this solution, this explicit solution, and calculate it, but we want to do it in an algorithmic way. And from this point of view, of course, we have this optimization problem, and there, if we have a W, which is not the correct solution, what should we do? We should improve it, and the gradient gives us the direction in which we should improve it. So this is why we do this. So the gradient gives the direction to improve an approximation. So now we say, okay, we don't know what the solution is, but we start somewhere. It's not the correct one, but then we are going to improve it by going in the direction of the gradient, or opposite to the gradient. Okay, so this means we start somewhere, starting from some W, 0, and then I iteratively improve it by saying that W at time t plus 1, okay, so those are just steps, so t is here the time, but it's just integer numbers. So this is the W which I had before, and then I'm improving it by adding a little bit in the direction of the gradient. And okay, I should go opposite, and I have to take, of course, step size, saying how much I should go in this direction, and then I take the gradient in the direction W of my quantity, which I want to minimize. And here, of course, I should consider this quantity at this W, which I had at time t. So I have here this squared. So I take the quantity of this guy, but then I take the gradient at this position. Okay, and that's a very general procedure, this gradient descent for optimization problems. And of course the t here, you should think of t as a time, but of course I'm just doing here integer steps. So t is just a natural number, but it corresponds to the time. And this eta, of course, you have to choose somehow, and this is somehow the step size, or maybe in the neural net context, the learning rate. So eta step size, or in the neural net context also called the learning rate. Good, okay, and now if you do this by general properties of such things. I mean, in the overdetermined case, where actually you have a unique solution, this algorithm will really converge to the solution. So in the overdetermined case, it's really everything is nice. So if you have a unique solution, and I mean, here we have actually a quadratic problem. So convexity is usually the thing which gives you all the tools for proving things. So we have here a nice convex problem, and then we have a unique solution, and then this algorithm converges to it. At least if you choose your eta small enough or in the right way. So in the overdetermined case, this converges to the only solution, which is the least square solution. To the least square. So really the solution which minimizes this guy here. And in this case, it's not equal to 0 in general. Good, but of course, in the underdetermined case, there are infinitely many solutions. So of course, I mean, it's not clear to which this converges. And in general, it will not converge to the best one. So we have an idea what is the best one. The best one is the one with the smallest norm. This here will converge to something. It will converge to some solution. But in general, this will not be the best one. And this is a reason that usually, I mean, one improves such algorithms by doing some kind of regularization. Okay, but let us maybe first look on an example, very easy, trivial example to see what essentially happens and what is the problem in the case that we don't, or to what do we converge. Okay, so let me do an example. And let me call it officially an example so that at least we get some number in this chapter 8.1 example. So I consider now a function which is totally okay. I mean, of course, the function f of x is of the form wx, but now I'm choosing the dimensions more or less as small as possible so that I still have an underdetermined system. So namely, I take the p equal to 2, but the n equal to 1. Okay, and so I have here wx, and so the x is a two-dimensional vector, and the components I denote by t1 and t2. So this is 2 tensor 1. Okay, so this means p is 2, but n is equal to 1. So I only have one observation, and the w. Okay, this is a vector in R2. I want to multiply it with a vector, so this also must be a vector in R2, and I want to get out a number. Okay, so the w has two components, and let me call them θ1 and θ2, because very often the parameters which I want to optimize are called theta. So let me call them θ1 and θ2. So this is just a vector, but now written as a row vector in R1. Okay, and so this means, of course, that my f of x is just θ1 t1 plus θ2 t2. Yeah. Okay, and now I'm given one value of my function f applied to some data vector. So assume now, so the information which I have, assume we are given that f at the vector 0, 1 should take on the value 1. Okay, so this means that data matrix X is just 0, 1. Okay, now you see that n is equal to 1. I just take one input vector. Okay, of course this was just my generic data matrix, and the y hat. So this is the the row vector consisting of all the observations, but I only have one observation, so it's just the 1 times 1 matrix. So it's just, I mean, it's just the 1. But here as a matrix or a vector. Okay, and then, so what we want, So we want to find the best W hat, which has the two components, theta 1 hat, theta 2 hat, such that the y hat is actually w hat times x. Okay, and what does this mean? This means, of course, so the y hat is just 1, and this is just this multiplied with this. So this multiplied with this is, of course, just theta 1 hat times 0 plus theta 2 hat times 1. Okay, and now you see, I mean, this is already set up in such a way that you see here very precisely how the situation is. Of course, I mean, this doesn't have a unique solution because, I mean, I don't have any information about the theta 1 hat essentially. But of course, in principle, this tells me that the theta 2 hat must be equal to 1. There I don't have a freedom, but I have the total freedom of theta 1 hat. Okay, and of course, it's clear, I mean, if I don't know anything about the theta 1 hat, probably I should set it equal to 0. And this will, of course, also be the solution where this vector has the smallest norm. Okay, so I mean, no unique solution, but somehow it's clear what the best solution should be. And of course, I mean, our general best solution prescription gives us, of course, this in this case. But maybe let us just check it. So our solution from before, so this was omega hat is, so this is y hat, or probably it's not, yeah, maybe this one, y hat times x transpose x to the minus 1 x transpose. So that's a general solution which we have. But in this case, so what is this? So y hat is just 1 x transpose times, okay, so what is x transpose? So x is 0, 1 as a column. So x transpose is 0, 1 as a row times x 0, 1 to the inverse times x transpose, which is 0, 1. And of course, so this here is now just the inner product. This is just 1, and the inverse, of course, is also 1. So this, of course, is invertible. So this is 1, 1, 1. So what we get here is 0, 0, 1. Okay, so this really gives us exactly the one solution which is somehow clearly the best. It clearly has the smallest norm. Good, but now let us look on this from the point of view of gradient descent. So say somehow, we can stare at this, but we don't know what to do. So we just choose arbitrary w at the beginning, and then let us check what gradient descent does. It should produce some things which hopefully converge to something. So, but now gradient descent. Let us look on gradient descent in this setting. So this means I have now WTs, which with components theta 1 at t and theta 2 at t, and I have the prescription that the t plus 1. So I get this from the previous WT by going with eta into the direction of the gradient of my y hat minus wt x squared. Yeah, okay, and of course we calculated the gradient, but it's not here anymore, the general formula. So the gradient of this thing, the general formula, so this was, okay, factor 2, and then we had the derivative of the quadratic term, which was wt, and then we had x times x transpose. So maybe we don't have it anymore. Maybe I write it. Let me write it down again. So our formula, the general one, w, the gradient of y hat minus wx squared, So this was minus 2 times, and then we had W XX transpose. No, so minus here, and then we have minus Y hat X transpose. Okay. So the first term is this W XX transpose at WT, and X transpose is now a matrix. X transpose X was a number, but now the other way around, this is just this vector times this vector, and this is just a matrix which has only a 1 here. And of course, this is a matrix which is not invertible. Okay, but yeah, but here we don't have to take the inverse, but so we get this. Yeah, and then we have minus the Y hat times X transpose. I mean, the Y hat is just 1, and the X transpose is just my vector 0, 1. Okay, and of course, yeah, so what I have here, so this here, maybe let me, so this is 2 times, yeah. So this is WT minus eta, and then here, what do I have? This WT is theta 1, theta 2 multiplied with this, but then you see in the first component I just get 0, I get 0, and in the second component I just get the theta 2. So this is here theta 2. Okay, and so let's put me the 2 out here, the 2 out here, and then I'm subtracting minus 0, 1. So this here is just this here, and I'm subtracting this. Okay, and so this tells me that the derivative or the change in the first component, actually there's no change at all, because I have a 0 here and a 0 here. So the first component doesn't change at all. In the second component, this changes, and this converges to the right thing. Yeah, so what we have is the theta 1 at t plus 1. So the first component of this, of course, is the first component of this. So this is theta 1 of t, and then I would subtract eta times the first component of this thing, but you see the first component of this thing is 0, so nothing is going to be changed. So this means this gradient is not able to improve on theta 1. If I have chosen this in the wrong way, I mean, I cannot improve this. For theta 2, of course, the situation is much better, because I mean there I should converge to something concrete. So the theta 2 at t plus 1, of course, is the theta 2 at t, and then I'm subtracting 2 times eta. Okay, I'm subtracting eta, and then I have the 2 from here, and then I'm subtracting the theta 2 from here and 1 from here. So I have here the theta 2 at time t minus 1. This one, okay, and you see that I'm going to have changes as long as theta 2 is not equal to 1. Theta 2 equal to 1 is the solution which I really want, which is the right solution. And if this is not yet achieved, then in the next step I will try to bring this closer to theta 1 of 2. And of course we can see that this iteration converges to 1. So maybe we should check. We also have to make the eta, change the eta in the right way. If we make eta much too big or so, then of course we might not have convergence. But so let us check this. So I mean theta 2 of t plus 1, we want to check whether this is close to 1. And so I'm subtracting here just the 1, so I can subtract it here. So I have theta 2 of t minus 1. So I have it here, but here I have it again. So what I have here is 1s from here, and then minus 2 eta. Okay, and so you see if this 1 minus 2 eta is less than 1, I have a exponential convergence to 1. Then this difference is getting smaller and smaller with the powers of this. So this this means theta 2 of t converges to 1, but of course I should have 1 minus 2 eta less than 1. Okay, so I should choose the eta in the right way. I mean, not too small. Okay, small is okay. Then it converges, but maybe quite slowly. But so should make it a bit bigger. Then it converges faster. But if I make it too big, then it doesn't converge anymore. Good. But the point here is that theta 1 does not converge, or it stays where it is. Of course, it converges. It's not changing, but it's not going to 0. 0 would be the best one, unless I have started by 0. So this means I'm not able to improve on the theta 2. So this means in general, if I just start with an arbitrary w here in the beginning, I will not converge to the best solution, not the solution with the smallest norm. I mean, I must have chosen my starting condition, my starting point in the right way. Okay, and maybe here in this case I know what is the best way and so, but in general maybe it's not so clear. And so maybe what one is doing is that one is proving on this by doing a kind of the linear regression, by doing a kind of what is called rich regression. One changes the iteration a little bit by also taking into account that my goal is not just to get exactly my equation right, but also to find a solution which has the smallest norm. So I want to minimize not just the condition that the equation is satisfied, but also the condition that the norm is minimal. And so this is what is usually called rich regression. So let me talk about this, maybe first a little bit in general, and then maybe we go back to this example again. And there, yeah, I mean there we are not just want to solve our equation, but we want to find a solution which has nice properties. Okay, and of course it's as an equation this is hard to say what this means, but we can put this into the quantity which we want to minimize. So essentially you're thinking of the quantity which you want to minimize, that's your loss or your penalty, so this should be as small as possible, so deviations from the smallest possible value are penalized. And in this function you can put in some quantities which describe somehow the smoothness or whatever properties of your solution which you want. In such a form, I mean, you have to put them into this such that you want this term to be small. Okay, so instead of minimizing, and let me now call it L. Usually it is called L. It's a loss or so. So in our case, this was the square of the norm of essentially our equation. Okay, so this equal to 0 means that we solve the equation, but now we know just solving the equation is maybe not good enough, but we want also a solution which is nice, and so we add a penalty term which characterizes or which penalizes large norms. So in our case, nice means the norm should be small. So we should have a penalty term for large norms. And this means, instead of this, we want now to minimize L, and I'm adding a term which depends on lambda, so I'm putting also lambda there, that I take, okay, the term which describes the equation which I want to solve, but then I'm adding something with this lambda, which is just the square of the norm of w. So if the norm is big, then I mean this term will be big. So I might have a w such that this term is 0, but then this term is big, and still this might not be the best thing I have here. Okay, and I'm doing this for some lambda bigger than 0, which the lambda is also something which I have to put into. Okay, and now of course this is now more or less the same kind of optimization problem as before. So we can do the same as before. We take the gradient of this. So for looking for minima for this, the gradient should be equal to 0, but now we have an additional term here. But this is again easy to deal with. So the minimizer of this is determined by, okay, so what we want is that 0 should be the gradient of this loss function at the point w. Yeah, for w hat. Okay, but let me write it in general. Okay, and of course, what is the gradient? So the gradient of this, okay, I tried to keep it, but it disappeared, but I think we still all remember. So the gradient of this, so of the first term, that was just 2 times w x transpose minus y hat x transpose. Okay, so that's just the gradient of this, and now in addition we get the gradient of this, but yeah, this of course is lambda times, and so we have the gradient of w, and this is of course just w transpose, and I mean we know that this is just 2 times w. That is, I mean, before we calculated this where I had a matrix in between. Now you can take the identity matrix in between if you like, but maybe you also see directly. Yeah? So you see we get here a perturbation of this term. So I have 2 times, I mean this goes nicely with this, so I have here w x transpose plus lambda times the identity matrix minus y hat x transpose. Good, and now you see, again, we have now an equation. So if we set this equal to 0, so this gives us an equation for the w. Let me, yeah, so so this equation, again, we can't forget about the 2, and then of course we get that this in the bracket should be equal to 0. Thus, we have that w hat. Let me call the solution of this again w hat. So x transpose plus lambda times the identity matrix is equal to y hat x transpose. Yeah. Okay, and now you see that we have regularized our problem. I mean, the regression itself was without this term, and then this equation we could not really solve in a unique way because x transpose was not invertible. But now, if I'm adding this lambda times the identity, this matrix here is now always invertible as soon as lambda is bigger than 0. Because this is a positive matrix, positive semi-definite, and this here is bigger than 0. So this means this here has eigenvalues which are equal to 0, but now I'm adding a lambda to them, so I make all the eigenvalues different from 0, and then it becomes invertible. So that's the main point, or that's, at least from a mathematical point of view, the nice thing that I have now really changed the problem, that I get a unique solution. And then of course, okay, then it's much better. Then of course gradient descent also, I would expect that it should converge to this one, if there's only one. If there are many solutions, then of course the problem is to which one should I go. But here, now, I don't have this problem anymore. So note, this is for lambda bigger than 0, always invertible. But of course it's important that lambda is bigger than 0, because this has positive eigenvalues. For lambda negative, I might subtract one of the eigenvalues which I already have here. Okay, but with positive lambda, I'm just shifting in a positive direction, and if I had nothing below 0, then okay, I just above 0. Okay, so this means I really can take the inverse of this, and I have now a formula for my solution. So this omega hat is this y hat x transpose times the inverse of x transpose plus lambda times the identity to the minus 1. Yeah, okay, and so this means we are getting now a unique solution. No? So, I mean, if I'm just choosing a lambda, I mean, I'm free to choose any lambda I want. I get now a unique solution, and of course, I have balance between two things. No? So this gives a unique solution, which, I mean, on one hand, I have given up the interpolation. I mean, it's not true anymore now that where is my I mean, I have minimized this whole thing here. Okay, but the minimization is not, of course, achieved at 0. So this means this guy here is not necessarily equal to 0. So I have not solved my equations anymore exactly. So this means I don't have here an interpolation. I mean, interpolation means that I'm meeting the points which I prescribe in my data matrix exactly. Okay, I mean solving this equation. But this is not true anymore. But usually this is not a big deal. I mean, usually, I mean, if my lambda is small, I will also still have here a small deviation. So usually this is not so bad if I allow this. But I'm going away from solving my equation exactly because I want I want to have other properties still. So this does not interpolate exactly anymore, but we allow small errors now. And this depends on lambda. Okay, but on the other hand, so I mean we lose here something, but maybe this is not so bad. But on the other hand, we gain something, and this is that we keep this norm here small. I mean, we optimizing this, so and of course this optimization is not achieved if this here is very big. Okay, so this means we are keeping this small. So here we have terms which control somehow the properties of the solution which we are looking for. I mean, very often you also involve derivatives in more general, so you want smooth solutions or so. You want small derivatives and stuff like this. So that's things you can put in such penalizing terms. This means that you look for solutions for which you can control this. Yeah, okay, and then we have here a unique solution, and then you can, then in principle you are back to your convex optimization problem where you have a unique solution, and then the gradient descent, I mean, it necessarily has to converge to this one. Okay, so the gradient descent, if you now apply it to this, it will converge to this solution now, which is not our best solution in the original sense, but it's the best solution for this regularized frame. So the gradient descent converges to this solution. Okay, and maybe you should note that actually if you send lambda equal to 0, then you will really recover the best solution which we had before. So namely, you should also note that this here is also connected with the pseudo-inverse. I mean, this is a way of defining the pseudo-inverse of a matrix just by, I mean, pseudo-inverse means it's not invertible. You can repair this by adding something which makes it invertible, and then you send this something to 0, and you hope that the inverse converges to something. And that's exactly what is happening here, because if lambda goes to 0 here, then in principle we would go to the pseudo-inverse of those things. So note that. So actually, if I take the limit, lambda going to 0, of what I have there, x transpose plus lambda 1 to the minus 1, that this goes to this x plus, which is the pseudo-inverse. You see, I mean, if this term is not there, and if everything is invertible, then of course this here is x transpose inverse times x inverse, and this would cancel this. This would be the inverse of x if x is invertible in a square matrix case. if we are in other cases, I mean, yeah, then this without a lambda doesn't make sense, but we can say we just take this, which always makes sense, and then send lambda to 0, and then of course one has to see that this converges to something, but it does, and this is the pseudo-inverse. Huh? I mean, there are many ways of defining the pseudo-inverse, but this is maybe a nice one, which fits very, very nicely with this linear regression. Okay, and from this, I mean, then you can also see that the solution which we get here, this rich regression solution, converges for lambda equal to 0 to the best regression solution. The one which I said is the one which solves the equations exactly and which has the smallest norm. So everything fits together very nicely. So this here is called rich regression. Of course, we are adding here something which I don't know whether this looks like a rich or not, but anyhow, the rich regression solution. So this is this solution here converges for lambda going to 0, of course coming from the positive direction, to the regression solution. The one from linear regression, where we chose the best one, so that the norm is the smallest one. Good. Okay, so maybe one could now go back to our example and check things, how they look there concretely, but maybe time is over for today, and so maybe I just leave it to you that maybe you can look for yourself and work out the details for this example and check that how it looks there. And also maybe in particular check that you really have a convergence to the best solution if you're adding this lambda. With this lambda, everything becomes nice. And you really converge to a unique solution. And then if you send lambda equal to 0, you converge to the best solution which we had before. Yeah?
Are there estimates for upper bound for that lambda?
Yeah, I mean, again, if you look on this example, then you see that if you want to have convergence, you should have a combination of lambda and eta. And of course, I mean, in more complicated problems, okay, there are also abstract estimates, but okay, I'm not sure how useful they are. But of course, it means a lambda. I mean, you have to ensure those things, these convergences. Of course, you have to choose things in the right way. Okay. I mean, you can choose lambda and you can choose eta. But of course, I mean, lambda usually you want quite small, because otherwise, I mean, if you put too much emphasis that you don't want small, that you want small norms, but you're not caring so much about your equation anymore, then maybe you get something which has nothing to do with your equation. So I mean, lambda is usually not is a quite small quantity. Okay, and then of course you must look for the eta, how to choose this. But maybe if maybe you can check this example in this case, and then you see at least there that the combination of eta and lambda plays a role for the convergence. Good. Okay, that's it for today.